Hello. Ooh, a lot of people. Thank you very much for having me. I just want to share my research, something I discovered, and for me, I find it really interesting. I will try very hard not to bore some of you to tears, but I am going to be moving very, very quickly. I've got way too much content. Just my favourite little video. Thought it was rather appropriate considering the topic. Right. I'm the Global Head of Hardware Security and Capability Development for IBM's X-Force Red. I didn't come up with that title. It's a really, really big mouthful. I spend most of my time creating hardware capability, offensive tools for IBM when the consultants need some capability or they need a piece of hardware that we can't get or is only available on the dark web, then I'll go ahead and actually build it. My alias is the toy maker, simply because that's what I spend most of my time doing, and that's a lot easier than simply spouting that long title. Some of the boring bits, because some of the content I'm going to be going through here is, I believe it would be irresponsible to tell you the companies affected by it and any other particular details, simply because they can't fix it with software. They have to re-engineer their products. As a result, the target component, as you can see, is just going to be referred to as component throughout the entire presentation. There are some company names in here, but they're not related to the disclosure. So to get on to the topic, I'll give you a very quick summary. There are some, I think I'm popping a bit, there are some IoT manufacturers that are taking very serious action to make sure that in the event of a software compromise, that the user's privacy is not affected. And I think that's really admirable. So they're actually building in hardware to make sure that, on the assumption that software can be hacked, when it is hacked, the user still has control over their privacy. And there's a particular component or series of components that's been used to make this happen. I'm targeting one particular one in this paper, this presentation, but the same research that I've done here, I have been able to apply in other contexts, and you'll see what I'm talking about. But this product, or this particular target component, just once again from a disclosure point of view, makes no security claims. It doesn't pretend to be a security product. This is all about a circuit board implementation, so how these products are being used at the circuit layer and how you can manipulate some of the physical properties by finding certain characteristics. But before I get into the fun bits, I thought I should do a little bit of a recap. Security as a design problem. We all hear about SDLC and secure software development, but if you're not familiar, in 1970, the DoD commissioned a report which was nicknamed or been named the Ware Report, and they actually state that you require, as you can see, a combination of hardware, software, communications, physical, personal, and administrative procedural safeguards is required for comprehensive security. In particular, software safeguards alone are not sufficient. I think the really key part of this is this was in 1970. We're still seeing in the industry a lot of people purely relying on software safeguards. And if your systems are stuck behind firewalls in a data center, that's probably fine. But in IoT space, embedded, automotive, people have effectively unlimited access to the target product, in which case you need to look at the holistic picture. I'm a firm believer that, I'm not saying that you should, but anyone who produces a product should be able to publish all of the information, all the schematics, source code, design documents about their product, and their product should still be secure because it's been engineered properly in the first place. Just a nice simple case study. This is actually an automotive one. The first thing we do in hardware security is you get given a product, you pull it apart, you find out all the components, anything that has data stored on it, you try and get the data off. We did this for a telematics unit in a vehicle, and you can see the little flash chip over on the side here. The manufacturer said, oh, that's fine, yes, you've got access to the file system, but what did you do? How did you do that? So, well, we used a data man reader and a flash chip socket. And they said, well, that's a couple of £1,000. That's a little bit of a barrier. I said, it's not a barrier. We simply do it that way because it's quicker. So to prove a point, now there's somebody in the audience who's going to heckle me for this one. I'm going to say I did it, but it's actually my wife because she's better with a soldering iron than I am. soldered 7 wires onto the bottom of the BGA chip, and most people don't realise that flash chips will actually emulate an SD card if they're wired up correctly. So 7 wires straight into an SD card adapter, stuck it into an SD slot, mounted the file system, got past all the software controls. So this system was well locked down, had good software controls, but all you had to do was pull the flash chip off to recover the entire file system. And a couple of hours and me going, come on, solder faster, I want to get on with this. But that's just a classic example. Once we had access to the file system, the rest of it fell. We were able to decompile Java, we were able to get access to the storage, any cryptographic material, and that was just to prove a point. Another very simple one. This one's a typical of security through obscurity approach. Once again, it's really difficult because the engineers, the electronics engineers and mechanical engineers always do such a good job. They're just not thinking like the devious people we all are. So when you actually explain to them some of the processes we go about to recover and get access to these systems, it makes a lot more sense. So this one was an Atom-based phone. It had quite good security controls in place from a software point of view again, but I'm being a very impatient person. I spent about 15 minutes trying to get past the software and decided this just wasn't worth the hassle. So I simply pulled it apart, a little USB microscope, and started looking over the circuit board. And I found that there was a small cluster of unloaded components. So to cut a long story short, those components are typically option resistors, which is how the developers choose whether or not the bootloader is to go into development mode or production mode. So one by one, I put one of these resistors on, reset the device, and went round and round in circles. I also found what I was pretty sure was a serial port. Put that on a logic analyzer, nothing happened the first few times. All of a sudden, I put on one of these components, reset the device, and a load of data spat out. And I put it into real term, as you can see there, it was the BIOS boot screen. So it was the entire terminal straight into the back end. There was no username, no password on the control. So once I had that, it's a little bit blurry, but I went in there and disabled UEFI secure boot. Then once again, I was able to get access to the entire file system. This was so easy because the parts are so small that literally with a screwdriver you could scrape the solder paste that's left over from the production process to actually bridge the part. So once again with a screwdriver, it was all that was actually required to get access to this development mode. So as I said before, I'm a firm believer that security comes from process. You don't choose security technology, you choose what your requirements are first. Once you know how you want to, what you want your product to do, how you want it to function, part of that should also be how you want it secured, then you can go ahead and choose technology. Anyone from an engineering background, we all love gadgets, we all love toys. Something new comes out, oh, let's use this to build a new product. That's not actually the right way around. So if you implement a proper process and make sure before any designs are done, your product requirements, functional, safety, security in bold, obviously, commercial life cycle. Part of the security requirements, obviously doing cover life cycle as well, end of life, that sort of thing. So, as I said earlier, a lot of these companies are assuming their products will be compromised. So if you assume it can be compromised, design it with that assumption in mind. So for a traditional data system, risks from compromise are typically to data availability. Let's just say for semi-autonomous systems or vehicles, you end up with a security risk that can actually have an impact to life, a safety risk. So if we look at the IEEE guidance on EMC and functional safety, it's a massive book, but this particular part I think is really, really important. Warning of a hazard is not considered a substitute for guarding against it, where guarding against it is possible. Guarding is considered no substitute for designing the hazard out in the first place, where it is possible to design the hazard out. So you're talking about anything embedded, it's really important. Where you can, design these hazards out. Don't simply tell people about it. So if we put this into context with an autonomous vehicle, telling a driver they may not have control of the car if someone was to hack it really is not a substitute for guarding against that in the first place. Conversely, adding edge security devices is not considered a substitute for designing the system properly so that in the event of a hack, the driver still has sufficient control to control the vehicle safely. And that's a hardware design problem. That's not a software design problem because you assume the software can be compromised. So I've done things with some automotive manufacturers where we've redesigned their steering controllers so that in the event of a software hack, the controller actually validates the human input over the top of the software input. So it's actually a relatively straightforward process. So now getting onto the topic, this is the bit which I get really excited about, so I had to get through that first bit. So as I said earlier, some IoT designers are taking really serious action, actually building in hardware. So you imagine the IoT devices where you've got a mute button. You've actually got a button to mute and unmute the system. You've got laptops with LEDs at the top to tell you when the camera is on. These are all things designed to make sure that we are aware when our devices are listening to us or watching us. So some of these hardware designs require, as I said, a user to physically press a button. So they've implemented that not through software, they've implemented that through digital logic. And that's what my little board down here is all about. The question that I asked them was, just because your logic's flawless, does that mean your implementation's flawless? And no, it doesn't, because of some of the physical characteristics. So if we look at the Failsafe Logic itself, once again, setting a little bit of scene, there's a lot of technical content here, so I'm going to try and move fairly quickly. There's this particular component is a very small mixed signal component. So it's like, if you're familiar with a tiny little field programmable gate array, so FPGA, tiny little thing. It's a small cluster of lookup tables and some comparators and a few other things. But it's really ideal for building these small state machines in. So this is the development board, and just to put it into context, you can see the USB plug on the left-hand side, and you can see how small the actual component is. It's tiny. I think it's 2 millimeters by 1.5 or 2 by 3, something like that. It's a really tiny little component. So this development board and that carrier board, I actually have that carrier board plugged in to my target IoT device, and I'll show you that later on. But that little tiny component is actually the target of my research on this particular instance. So what it does, these mixed signal logic, they have a series of gates. So you imagine the whole thing is just a matrix. You connect columns and rows and actually form a small circuit inside that. And depending on what you want it to do, you connect those circuit paths to, as you can see, a lookup table. That lookup table is functionally an AND gate, so anyone familiar with electronics is aware of what I'm talking about. And then you then route the output. So once these things are programmed, they can't be changed. So you're actually defining this logic inside. So that's a screenshot from the actual designer software. So you can see we've got some AND gates. So the blue parts around the outer edge are inputs and outputs. You can see by the direction of the arrows. We've then got all the grey parts, which are the configurable logic. So depending on how the signals are actually made, you simply draw draw all these lines, draw up this nice little schematic, and then you can test your logic. So the logic of this one is that the user has to press a button to disable privacy mode. So the software can put the system into privacy mode, which is fine, as in it can turn off the cameras and microphones, but the user has to press a button to re-enable it. And that's done through the bottom path, which is there's a button debounce, there's a latch in there, and some other bits and pieces. And you can also see that the privacy LED on the right-hand side, you've got camera, microphone, gate enabled, and then below it, privacy LED. So they're actually running separately, which is really important, so that, the logic itself, because they might both run at different voltages or different characteristics, and you might want them one to be inverted, one not to be, but those two are both actually run. So in the event that the camera turns on, the privacy LED, because they're actually two different functions. So this software can also turn it on and off if it needs to, if it doesn't have a reason to, but the minute you press the mute button and the software enables privacy mode, there should be no way for the system to listen to what you're doing or see what you're doing without you pressing a button. So I said this is the bit that gets a little bit dry, so I do apologise. This is a typical data sheet. This is a data sheet from one of these particular products. Anyone involved in hardware security, the first thing you do is you go to the data sheets, you have a look, see what the manufacturers say the actual tolerances are, see what the voltages are. Anyway, when I was doing this research, this was many years ago, the first thing I did was look at this, and I saw, well, there was a couple of gates, so there's a couple of gates in the chain. One particular gate, if you see here in the middle, at 3.3 volts, the center column there, to change from a 1 to a 0, or a 0 to a 1, takes these little gates 15 nanoseconds. That's pretty quick. But when you add them up, to change from a 1 to 0 to back to a 1 again, that's 30 nanoseconds. All of a sudden, that little gate can only handle 33 megahertz. So you've got a total bandwidth of 33 megahertz. And then I started thinking, what happens? We've got two of them together. What happens if I go above that frequency? Then these things are not designed to go quickly, but they're connected to a very powerful processor that can make these changes very quickly. Once again, a little bit more context, so I do apologise about this. With any electronic component that's manufactured, in fact, any manufacturing, there's a manufacturing bell curve. In the data sheets, they say typical. So typical is that red line. That's where most things should actually work. Then you've obviously got the low end of the spectrum, you've got the high end of the spectrum. with these sorts of resonance attacks, you will find that you may, depending on what sort of voltages you can get out, you may find that your attacks work on typical and below, but won't work on the higher end because the thresholds are slightly different. There's a lot to actually consider, but because this is all about manipulating physical properties, you have to understand exactly what you're looking at. So once again, you can get these manufacturing bell curves and these tolerance curves from the manufacturers. So if you're trying to do one of these sorts of attacks, it's you characterize your target, you then go through and find all the data sheets from all the parts and actually put together a chain to work out best and worst case. So without boring you too much, that's the picture. I've reproduced it again. And then underneath it, this is a very, very simple logical version of what I've got, my little board here. So you've got the microcontroller, you've got that logic, and you can see a little physical button there. And then there's a load switch. Now, the load switch is simply to turn the USB power on and off. Because I've seen some of these systems where they actually have a USB camera and microphone, so they simply turn the power off because they think they're doing the right thing. Turn the power off, you can't hack it if the power's off, which is really good. So they also turn off the data, but that's controlled the same way. So my objective is, or was, can I turn that load switch back on through software, even though the hardware's there to make sure that no matter what happens to the software, unless the user presses that button, the camera and microphone should stay off. So obviously, I wanted to understand what happens. So as I said earlier, my question is, what happens if I exceed the bandwidth? So what happens if I start sending a signal out that's faster than what this little chip can actually handle? So some sciencey stuff, really technical. An inductor is a small passive electrical component that stores energy in a magnetic field. More often than not, it's just some copper wire around some sort of ferrite core or something like that. I put all the equations at the bottom because I thought they looked cool and made the slide look really cool. There's a lot of maths behind it, and that's really dry. But we'll get on to some more sciencey stuff. You can see I'm really creative in my slide titles. Delta voltage, delta time. So anyone who deals with electronics is aware of the fact that a 1 and a 0 isn't actually a 1 and a 0. When you change from a 1 to a 0, there's the infinite ranges of voltages in between as the signal actually changes. The rate at which this change happens is called delta voltage over delta time. It's how fast the voltage changes over the period of time. So the top one there shows you, obviously, time and voltage. So if you look at a simple clock signal, it looks like a 1 and a 0. And in software, it is a 1 and a 0. But the electronics has to change from a 1 to a 0. If you zoom in on an oscilloscope and actually have a look at any clock signal, you'll see something more like the one at the bottom, where they're actually on an angle. So when you're designing products for EMC compliance or whatever else, you need to slow those curves down because every time that changes, you get a small amount of emissions. And to get those emissions down, most EMC electronics designers will actually slow those curves down. Most of these IoT products, they're not designing for that purpose, so they have really, really sharp edges. And it's actually those sharp edges that cause the problem. That's what that's my theory anyway. So we'll get on to a little bit more context. An analog switch is like a relay, except there's no parts. So it's an electrical component that allows electricity to flow either way when it's turned on, and when you turn it off, it stops. So when I was mentioning earlier about those that matrix, all those little points where the columns and rows join is actually done by an analog switch. Now, analog switch is really important. It's not a digital switch, it's an analog switch. That means it allows analog voltages to come through. Now more electrical stuff, once again, really creative with my slide titles. A charge pump. A charge pump in electrical terms is where you have a signal that's changing rapidly, and you're actually able to use that signal to charge capacitors via diodes, etc., and reach a higher voltage. And that's actually really important. There's a parasitic charge pump in some of these systems that if you keep these systems moving fast enough, you can actually reach a higher voltage internally than they're expecting. So back to this is actually a scope trace, just to show you. The blue and the yellow are actually in millivolts. What are they? I think they're 20 millivolts per division. So they're tiny little voltages. And normally, if you're looking at a system, you wouldn't see these. It's only because I was specifically looking for it. The green is actually on 500 millivolts per division. So that's a clock signal. Now, on an oscilloscope, I noticed that when the clock signal changed, and this was under normal conditions, if I captured it correctly, I could see a very small output following. So through this logic system, I noticed that there was a very small output that followed on the edge. So as you can see, green goes up, the yellow and blue go up. That's two of the outputs from this particular target device. When the green goes down, blue and the yellow go down, but they're going below ground. That's not a digital signal, that's an analog signal. And I thought, oh, that's really interesting. So once again, you have to have an oscilloscope to find this. So I used a signal generator, and then I started to increase. So I set the signal generator up to be the same characteristics, same impedance as the processor, and I started winding up the frequency. When you start to approach the resonant frequency of the particular target, the amplitude goes up. So you can see the first one, I think, is a bit hard to see from here. It's 2203 megahertz, 2252 megahertz, and you can see we're starting to form a sine wave, and you can see the amplitude is going up. This one is 23.36 megahertz, and it's near as matters a perfect sine wave. So we've found the resonant frequency of that particular target. So at 23.36 megahertz, that target was actually resonating. So those tiny little signals that were earlier on were just in millivolts, and if you're doing a normal logic design, you'd never notice them because your scope's not, you haven't configured to capture that. You hit the right frequency, constructive interference, and you start hitting this resonance. Then we go above it, we're at 23.9 megahertz, and the amplitude is dropping off 25.9, and it's really starting to fall off. So once you actually model the characteristics, you can start to find the resonant frequency, and then, of course, what we need to do is reproduce that. So we have a quick look at the target. That target is here on the board, on my table. So standard sort of IoT device, but rather than having any Wi-Fi or anything else, this is literally just so I could test the AC characteristics of it. So I simply include a USB to serial interface. Normally that would be a Wi-Fi module or something. How you talk to it is completely irrelevant. We've got the switchable USB. So the actual block in the middle, the purple block, is the actual target component. We've got the microcontroller in the middle. This just happens to be one of the microchip MIPS cores. And then the component interface. Because this component's so small, I can't solder it, not without using pick-and-place machinery. So it's a lot easier when you can program them once, you program it, you bring the carrier board across. So the fact that I'm using a carrier board as opposed to the chip directly on there changes the AC characteristics, and it does make a small change. But the same thing happens if the chip's directly on the board. It's just a slightly different frequency. So it's a matter of finding that frequency. So that's the picture. That's the little board which I designed. Loads of test points so I can see what's going on. You can see the little carrier board sticking up from the right there. I put in those switches, those dip switches, so I can turn on and off the signals from the microcontroller. I can also include some slew rate limiting resistors in the path to show that simply by putting a resistor in line actually solves the entire problem. So that's that. It's connected to the PC. That's the same docking station as I've got here. So if we go through that, that's the little board. We've got the FTDI chip for providing a USB to UART interface. We've got the MIPS core. We've got the component adapter, and we've got the switchable USB, so that I can reproduce. The reason I did this is so we can reproduce this attack without mentioning any of the products that are actually vulnerable to it, because like I said, that would actually be irresponsible, because the only way they can fix it is to redesign it. So anyone else can reproduce what I've done. I just simply did it all using Harmony. Literally pick the chip, pick the framework, went through and configured all the bits I wanted to do. So there's nothing particularly clever about this. Use their configuration tools to configure the processor, turn on the framework, turn on the serial drivers, turn on the console. So basically using existing framework to build it all. The other reason I did this is that this is a very common approach. You see a lot of people building IoT devices much like this. The frameworks are fantastic. They make it easy. Why write all this code yourself when you can tick a few boxes and it generates it all for you? It's another reason I did it this way. So you can't really see that, but that's my console handler. So I had to write that bit itself. But there's a buffer located actually meant to say on stack. I didn't proofread that properly. And then there's in the middle box there's the UART buffer read. So that's a function provided by the framework to read the serial buffer. If you look at the serial code itself, it's an unbounded write. So it's an unbounded write to the calling functions stack. So if I was to send in the wrong payload or whatever else, I could actually overflow the calling convention, the calling function stack, get my remote code execution, which is how you can actually make this sort of attack happen. Once again, this is just an example. This happens all the time, and when you're doing code reviews, you see this sort of stuff. Yes, you can fix that, but the assumption is that the software can be hacked. So I'm just literally put that in there for that purpose. dummy IoT interface, so it's just a little terminal, and I'll show you that in a little bit. That just allows me to, if you can see that, enable to turn the power on or off, so enable or disable. The minute privacy mode is enabled, that stops me from turning the power on and off because until the user presses the button. So basically, the software can enable privacy mode, which means the software no longer has control over the power. The user has to press a button from that earlier logic, which then allows the software to actually turn the power back on. I think that's quite straightforward. You can't disable privacy from there. So what I've actually got is a little video here, simply because this room's very wide, but if I've got time afterwards, I'll do the same thing on my computer right here, but this is just so everyone can see it. Is that going to start? Yes. Okay, so I'll just talk through this. That's just a Handtech USB oscilloscope. I've got the two traces, this including the autofocus thing. It's a little bit of fun. So I'm trying to set this up properly. Now, on the device itself, you've got the power LED, as you can see down the bottom there. There's also another LED that says when privacy mode is disabled, so that means that the system can potentially be listening to you. Oh, I'm actually talking through here as well. I'll just mute that. So if I press the button itself, as you can see from there, you can see that second light actually turns on. So that's a fairly typical sort of workflow. You press the button to unmute. The system then says, I'm potentially watching you or listening to you. And to simulate that, I've got a USB light here as well, just to show you. Once again, all I'm looking at is power. I'm not looking at the data. And you can see on the oscilloscope that the yellow and the blue voltage both went up. So the blue voltage is at 5 volts there, and the yellow voltage was at, I think, 3.3, which is the target voltage. So then with the software, I can enable and disable it at will. So if I skip to, where's my mouse? Back here somewhere. Okay, so if I actually run the exploit, you can see that now all of a sudden, well, that's just because the Earth probe fell off, you can now actually see that it's not a 1 or a 0, and if you look on the left-hand side, you can see where ground is. It's actually above and below. So there's actually the resonant output by sending in the clock signal at 70 megahertz, the yellow line is actually oscillating. That oscillating has a charge pump effect, which actually turns the system back on. Once again, you shouldn't be able to see that. That shouldn't work. And if the frequency is wrong, you barely see a glitch. You get exactly the right frequency, and the entire thing starts oscillating. So I've got a few theories. Like I said, I'm not 100% sure as to what's causing it. There's probably going to need to be some much smarter people than me looking at the problem to identify exactly what's causing it. But it's really easy to solve, so it doesn't really matter. So if we look at the edges, the green clock signal goes up, the output goes up. The green clock signal goes down, the output goes down. So this means that there's a distinct coupling between the input and output signals on the edges, and only on the edges, when the privacy hardware is operational. The faster that slew rate, or the faster the change in voltage time, the larger the output is. So this tends to indicate a number of different things. Now, I've had lots of discussions with lots of people, including some RF engineers who came up with some other potential theories for why this is happening. So I've included all the theories that I've heard so far, and I think, honestly, it's probably a combination of them all. So I talked earlier about an inductor just being not much more than a copper wire that stores energy in a magnetic field. So this one, if you look at my very early diagram, the analog switches join effectively two or three or four lines together. That is potentially an inductor, depending on the path. If it's actually looping round back on itself, that's an inductor. Then you have something called parasitic capacitance, which is the natural capacitance that any component has at a certain frequency. You put those two together and you get what's called an LC circuit. An LC circuit has a natural resonant frequency. So that was my initial thought. But the actual resonant frequency of a circuit that small is going to be up into the gigahertz, and I'm nowhere near that. So that could be part of it. Like I said, I don't entirely know. This is my theories. But it's possible that the parasitic capacitance of other parts of the board, how it's soldered on, etc., have reduced that frequency quite a bit. An RF engineer said to me that he thinks this might actually be partially an RF strip line. And he said you might be getting reflections. So at the right frequency, you're effectively ending up with either end of this small inductive loop at different voltages, and you do it fast enough, you end up getting RF reflections. I thought, okay, that might make sense. Once again, if you get them at the right frequency, coupled with everything else. And I think the main thing is that there's parasitic capacitance on the inputs, and there's also a ground bounce. If we hit it at exactly the right frequency, I think the parasitic capacitance and the ground bounce is we're driving this chip so fast that it's actually bouncing above and below ground. Therefore, the outputs are simply following it. And as it's all analog switch based, we end up with this AC signal coming out. The observation that I noticed is that the capacitance does change the resonant frequency. So if you touch part of it, the resonant frequency does change. So it does very much indicate that there is a capacitance there. If you change the decoupling capacitors on the thing, it changes the resonant frequency. It doesn't stop it, but it simply changes the frequency. So I think there's a lot going on. So just going back to this slide again, as we approach the resonant frequency, the amplitude goes up. We end up with a near perfect sine wave, certainly for this purpose. You can see it's not a perfect sine wave for anyone who's particularly detail focused. It's pretty close. So the next part I needed to understand is, why is this turning on the USB switch when the USB switch says it requires a minimum voltage to actually enable the output? So I started looking through all the data sheets, and of course the manufacturers aren't going to tell you exactly how their chips work internally, but with my best judgment, talking to a couple of engineers as well, we came up with a number of different simulation models that we thought were pretty close. They had the same basic characteristics as what the data sheets were describing. When we actually modeled, and this is just one particular one, you can see the green trace along the bottom. When it starts resonating, we actually end up with the parasitic capacitance of the gate of the FET at the top actually playing into effect of this. We're actually charge pumping that capacitor, so the switch, the logical switch, the FET at the top, has its gate has a capacitance in it. We're actually using that, storing energy, and slowly pulling it down, which is where you can see the purple signal. The purple signal. So as we reach, all of a sudden we reach the on threshold. So we're charging it frantically. If we keep charging it, it comes down. Then when it reaches the on threshold, you can see the red line all of a sudden starts to go up. Now, if you were to turn this on normally, that red line would be near as mad as vertical, and that blue line would come purple line would come all the way down. But because of the characteristics, and we're using the charge pump effect, we can turn it on slowly, well, relatively slowly. From the time you actually start the attack to the time this turns on is still only 5 microseconds, so it's still pretty quick. So that was all research I did without using the software. That was with signal generators and everything else. Oh, this is an interesting characteristic. It's not really very useful unless it can be done via software. So then, of course, how do you actually get these exact frequencies out of microcontrollers, etc.? So this was a software exploit for one of the versions of this board. Most of the microcontrollers, if you're familiar with them, they have the processor core. They then have peripheral hardware. They have output comparators, all sorts of analog lovelies, and they've got pulse width modulation hardware, all that sort of stuff turned on or enabled. The exploit, what it needs to do is to turn on this hardware. So it turns on this capability, adjusts the relevant divisors, and then you get exactly the right frequency. So as long as your clock signals 50% duty cycle and you can get the right frequency purely using the hardware. So the CPU core is not actually involved in this. All it has to do is run this code, configure the peripheral hardware, and then you're away. So I've come across some of the CPUs where their actual GPIOs can only go to 25 megahertz. And they're like, well, our CPU simply can't go to that. But what you can do is you can drive 2 signals out of phase to each other, and you can double the effective frequency. So there's all sorts of funny things you can actually do to actually, you don't have to have a perfect sine wave. You can find the right sort of combination of input signals to these devices. You can create the AC signal with a high enough RMS above ground to actually turn these systems on. So once again, this is all based around the assumption that the software has an RCE of some sort, which is the assumption that these products are being built around. Hence, they put the hardware in. So turning that into assembly language, 32 instructions, 128 bytes of code. If you can inject that into a buffer overflow like I showed you earlier on, you can configure the hardware. The system can continue running as normal. You've simply reconfigured some of the peripheral hardware to enable this exploit. The output stays on, but the LED itself never comes on. So the user is completely unaware that the system has actually enabled the camera, microphone, or whatever else. So this particular device here, I captured it on a scope and set the triggers up properly. And you can see that once again, the yellow signal, the voltage at the bottom, it says 1.3 volts. That's not correct. That's just because I had to zoom the time base out so far. It's about 750 millivolts, something like that. But once again, you can see the output actually drops slightly because of the charge pump effect. So we're actually pulling the whole system down slightly below ground. Then we charge up the output, we charge up the gate capacitor on the high side FET, and all of a sudden it turns on. But you can see it's quite a slow turn on. Anyone who's familiar with electronics, that's quite slow. But it's still turning on within 12 microseconds, and that's quite a slow edge. It's not all as bad as it seems. So we just summarize it quickly. You've got the change in voltage. So the rate of change of voltage has a big impact on this. So that means it's actually really, really simple to stop. If you reduce the speed at which the voltage can change, this attack goes away altogether. And that's part of the problem. That's why it's unpatchable. You can't do that through software. Because if you can change it through software, it can be changed back through software. All you need to do is actually put just a simple resistor in line with all of your logic signals going to and from any of these devices, just like you would with software. Your software controls, OWASP, validate your inputs. Hardware needs to validate the controls from other parts of the hardware system. Make sure that the maximum input frequency of your devices is adhered to. So if you've got a really fast CPU, like the one I'm using here, that can generate these signals, make sure that anything it's talking to, you've validated those inputs. You've slowed the signal down so that no matter what the software does, it simply cannot exert that level of control. So going back to it, the purpose of this hardware state machine in these designs is to make sure that when the software on the main processor, assuming it can be hacked, to make sure that the user still has control. The risk is that these designs, because their logic is flawless but the implementation is not, that the hardware actually serves very little purpose. It's good, it looks good, it's nice, really fantastic. These companies are building it in and they should be commended for that. The problem is that software can manipulate them if you spend the time and actually understand the target. Every model of device would have a different resonant frequency. Every manufacturer would have a different resonant frequency depending on how they've designed it. But once again, once somebody did the research and actually targeted these particular systems, it's just a matter of doing a simple software exploit to actually turn this back on. So there is some stuff we can do through software. I said software alone can't mitigate it, which is true, but there is some things you can actually do. Now, depending on the processor, etc. So there's nothing we can do about the silicon level stuff because that's outside of our control. Anyone doing hardware design, you have no control over what the companies are providing to you. The faster the slew rate, the faster the change in voltage over change in time, the greater the output amplitude. We can do something about this. Simply put a resistor in line. Now in production, these you're going to talk fractions of a cent cost differences. It's completely immaterial if you do it when you're doing the design. If you wait till after the design, you have to do a re-engineer. It gets very expensive. It probably ends up tens of thousands of times more expensive because simply adding these parts is at the design time there's no cost to it to speak of. Now, I just dropped out then. Hey. The signals that are under software control, you can do some hardening depending on the processor that you've actually got. So I'll talk about this particular MIPS one. So if you do some hardening and make sure that some of the hardware security capabilities are turned on. Now the really obvious one is on this particular chip, you can make sure that those pins can only be changed purpose once. So if they've been set to GPIO, you can say, do not allow these to be turned to an output comparer or pulse width modulated pin later. That's fine for the RCE running in this instance, but if it's a persistent RCE and you can actually restart the device, then that doesn't serve any purpose. But it's a countermeasure. It can help. It's all about defense in depth. Try to make the thing more difficult. The other way to do it, once again, is a redesign issue. On the microchip parts, they call them RP pins, as in remappable pins. You can change the function. But there's a lot of pins that are not remappable. So if there's something particularly security conscious that you want to make sure can only go at certain speeds, no matter what the issue, don't use a remappable pin. If it's remappable, then it means it's got this additional hardware connected to it that you can change through software. So you can see here, I've just picked a couple of pins. The RPE means that this is port E, it's a remappable, and it's bit 5. You don't want to use that if it's particularly critical. The pins in green, they're not remappable. Well, technically they are, because you can see there's analog, there's a parallel port, and there's GPIO stuff on there as well. So you could potentially remap that, just those pins, into the parallel port and do something similar with DMA. But once again, it makes the thing more challenging. But there's always ways around it. The simplest one is to simply add resistors in line. And to show that, once again, a really, really simple simulation. So if we assume a parasitic capacitance on the FET gate of, say, 5 picofarads, which is fairly typical for some of these P-channel FETs, You can see the blue signal. You can see we're getting a nice large amplitude. The minute you put a resistor, that R1 in line, the amplitude drops to that little green trace. That's all it is. It's as simple as putting a resistor in line to change that slew rate so that we don't end up with the same amount of current going through to affect this charge pump. So a summary of all of this. Some of these implementations are vulnerable to resonance attacks. There's a lot of characteristics, but with any sort of side channel, it's all about characterizing the target. If somebody has used a particular component with a very high, a logic high for actually enabling it, that may not be vulnerable. I haven't researched all of these options, but I'm not going to say they all are because that would be completely irresponsible. A lot of the modern systems on a chip or microcontrollers can generate signals fast enough to exploit this behavior. Like I said, even if the front side will only go at say 25 megahertz, by running two of the pins out of phase to each other, you can actually generate the right sort of signals that you're looking for. You can also do some funky things with DMA and actually changing the tri-states as well, so you can float pins and pull them back down, so you end up with some of the doubling effects. The other thing is to use the one-time configuration fuses if they're supported. So if your chip has the ability to set some of this stuff up permanently, then use that capability. Because if you don't use that capability, somebody can actually exploit this through software. Now, I'm going to try, I'll put that onto that one, but I'm going to do this first. It's going to pong and bing, and if anyone wants to come and have a look, you're welcome to. Get my mouse working. Oh, and of course, it's suspended. Well, that's going to slow things down a little bit. Well, whilst that's resuming, does anyone have any questions whilst I try and set this up? Wow, that's quiet. Either everyone's asleep because I bored you all, or no one wants to ask a question. Is this like waiting for a kettle to boil? It's not even that big a virtual machine.
Hello, sorry.
Right.
Have you looked at the power output of the circuit while it's resonating in terms of emissions? So does it, at resonance, also have higher emissions?
Yes.
That could tell you about something about the system?
Yeah, actually, that's a really good point. I did notice I used a waveguide antenna, sort of an SDR and a spectrum analyzer, and when you actually hit this resonance, you do definitely see a spike at that particular frequency. Obviously, I don't have the equipment to see exactly what's going on inside the chip, and it's sort of the area around that particular component is definitely resonating at that frequency. Yeah, on the spectrum analyzer, it's quite loud. But it would certainly be a good way to explore this a bit further. All right, let's see if this will work. You can see my little scope on screen. No, I don't want you to go full screen. Can somebody please tell Microsoft to stop doing that? All right. And I thought it would be a good idea to show this live. What a muppet. And connect that one. All right. All right, so we got that there. Is that connected? Yes. Okay. So if I press the privacy enable button, you can see that this light here turns on. So that's simulating the USB power. So turn that around so you can see that's on. Try not to blind anyone. If I tell the system to disable, the light did turn off. Sorry, I saw a reflection. I was like, huh, it's not turning off, but it's the light over there. So I can enable and disable it from here. And you can see the scope traces behind me are going up and down as well. So if I enable privacy, they go down. And obviously, the software itself says privacy mode's enabled, but you can't do that. But the actual logic in this little device here guarantees that. So now, where's my little program? Connected, jolly good. Okay, so if anyone wants to see, the privacy LED is off, saying that the system cannot watch. So I can try power on, power off, nothing's happening. If I then do the resonance exploit, the lights turn back on and you can see the resonance signal. You can see the signal at the bottom there. That is enough to create this charge pump effect to actually turn the system back on. So you can see that the lights are actually on. I can then clear the exploit, and if I turn on measure on source 1, let's look at peak to peak. So I'll go back through it again, press the button. Okay, and power on. It's really hard to see that that's actually on from here. So power on and power off, and you can see that that's all working there. So I'll enable privacy mode again and turn that back on, and you can see we've got peak to peak of 780 odd millivolts, and you can actually see it's actually slightly below ground, but that's enough to create the charge pumping effect to actually turn the system back on, and that's purely through software. So and most people are still awake. Wow. Thank you very much for having me. Like I said, it's just some research which I find fascinating, so hopefully it's of interest to you all as well.